record. Okay, today we will start time response because we have completed the chapter 2, modeling in the frequency domain. Okay. Is it clear to you guys?
Yes, sir. Yes, sir.
Okay. This is time response. Okay. So if you complete this chapter, you will get the idea regarding this, like poles and zeros of transfer functions to determine the time response of a control system. Describe quantitatively the transient response of the first order system and general response of second order systems given the pole location, and find the damping ratio, natural frequency, find the settling time, peak time, okay, overshoot, okay, and approximate higher order system and system with zeros as first or second order system. Okay, up to these things you will understand. Okay, so first of all, we need to know the concept of poles and zeros. See, here there is a definition of poles. See, the poles of a transfer functions are the values of the Laplace transform variable is that cause the transfer function to become infinite. That is the definition. You can write this. Please note this definition. The poles of a transfer functions are the values of the Laplace transform variable is that cause the transfer function to become infinite. See, the value of s for which the transfer function become infinite. Okay, that cause the transfer function to become infinite. The values of the Laplace transform variable is that cause the transfer function to become infinite. That is the poles. The value of s is known as the pole. Okay, so if another thing happen, other thing happen, if the transfer function becomes 0, then that is called the zeros. See here, the zeros of a transfer function are the values of the Laplace transform variable is that cause the transfer function to become 0. See this. The zeros of a transfer function are the values of the Laplace transform variable is that cause the transfer function to become 0. You do understand? So two things, poles and zeros.
Yes, sir.
Okay. So what we are dealing with? We are dealing with the transfer function, right? So if the transfer function becomes 0, then you note down the value of s for which value it becomes 0. So that value is known as the zeros. So if I ask you about the definition of a poles and a zeros, I think you will be able to give it, right? So this question sometimes come in the some job viva or job exam. Okay, if you attend the job exam, any type of job related to the engineering job, then they may ask you this question. Or if you do the postgraduate, that means the masters, then they may ask you these questions. Okay, so poles and zeros, these are the important thing in the control system. Okay, so is it clear to you guys? Poles and
Yes, sir.
zeros?
Yes.
Okay, thank you. Now we can move. Poles and zeros are there. Okay. They give example. You see here. Okay. Now look at this one, this figure. So this is what? This is actually S plane, right? This is S plane, S domain. Here, this is the real value. This is the imaginary value. J omega. J omega means imaginary value. Sigma means real value. Now, here, put the value of S minus 2. If you put the value of S minus 2, then it would become 0. All right. Now, see, we have S plus 2 divided by S plus 5, right? Now, if you put the S is equal to 0, then it would become 0 plus 2. Sorry, S is equal to what I am writing? S is equal to minus 2. S is equal to minus 2. If you put the S is equal to minus 2, then it would become minus 2 plus 2 divided by minus 2 plus 5. So it would be 0 divided by 3. That means what? If you put the 0 divided by, so it would be 0. Okay, it would be 0. It would be 0. So if you put the value S is equal to minus 2, then the transfer function, this is transfer function will be 0. So here you will write the 0. Again, if you put S is equal to minus 5, S is equal to minus 5, then what would happen? Minus 5 plus 2 divided by minus 5 plus 5. So it would become minus 3 by 0. So that would be infinity. That would be infinity. So if you put the value minus 5, then it would be infinity. So that is the pole. So pole is minus 5. That is pole. Pole is minus 5. And minus 2 is the zeros. Okay. You understand? Guys, are you there?
Again, sir. Again, sir.
Okay. So poles and zeros here. Okay. Let me show you another example. Let's say S plus 4 divided by S minus 8. That is your transfer function. Okay. So if I ask you determine the poles and zeros. Okay. So here what would be the pole and what would be the zeros? If I put S is equal to minus 4. If I put S is equal to minus 4, then transfer function would be in the upper side 0, in the lower side minus 12. That would be 0. So S is equal to minus 4. Maybe here minus 4, it would be 0. And if I put the S is equal to 8, then it would be infinity. So S is equal to 8 would be pole. See, this is the zeros and this is the pole for this one. So you write the zeros as 0 like this, and you write the pole like this.
Okay, sir.
Okay, understand? So 0 is cross. Sorry, poles cross. like this, and zeros like zeros. Okay, there's the thing. Okay, let's see here. Uh, that is the system 0. This thing is system 0. That is system pole. And that is the input pole. 1 over S. These things are known as the force response, natural response. Okay. Now move on to the first order system. So you get the general idea of the poles and zeros. Now move on the first order system. First order system means power of the S is 1. In the second order system, power of the S would be 2. Third order system, power of the S would be 3. Okay, so that is the first order system. So in the first order system, let's look at an example. Let's take example here. RS is the input, CS is the output, and GS is the transfer function, which is A by S plus A. RS is equal to input, CS is equal to output, GS is equal to A by S plus A. Okay. So here, now see, we know what? We know that transfer function GS is equal to output over input, CS by RS, or we can write the CS as the GS into RS. Okay, C is equal to GS into RS. Okay, we can write CS is equal to GS into RS. Okay, that is a thing. Now, so if your input is 1 over S, then what would happen? So input is 1 over S. RS is equal to 1 over S, and GS is equal to A by S plus A. A by S plus A. In that case, it would be A into S. A by S into S plus A. Okay, that is your equation. That is your CS. CS. Now, if you take the, okay, now you need to solve it. You need to solve it by partial fraction. Okay, so you can write what? You can write like this. So it's two part. A divided by S plus B divided by S plus A. Partial fraction. We are taking the partial fraction. Now what? Now multiply it by S into S plus A. Then A is equal to this A into S plus A plus B into Yes. Now put s is equal to minus 4, then is equal to, what would happen? A is equal to minus 4b. So b is equal to just a minute. Okay, so a is equal to minus a. Let me write that. Okay, now say s is equal to minus a. Okay, s is equal to minus a. So if you put this one, then what would happen? A is equal to, this one would be 0 minus ba. So b is equal to minus 1. Again, s is equal to, if you put the s is equal to 0, then what would happen? A is equal to a. So therefore is capital A is equal to 1. So finally, what you can write instead of this you can write CS is equal to A by S. That means 1 by S minus B 1 over S plus A. So if you take the inverse Laplace transform of this, then instead of 1 by S, you can write the 1. And instead of 1 by S plus A, you can write e to the power minus 8. Okay. That is the thing. They have not discussed this thing here. They skip this thing here very carefully. Okay. Now see here. Now what would happen? Let's put the value, some values here. If I take t is equal to 1 over a, then e to the power minus 1 would come, that would be 0.37. So 1 minus 0.37 is 0.63. Okay. So see equation 4.6, equation 4.7, and equation 4.8. Three things come here. 1 over a is known as the time constant of the response, and the time constant can be described as the time for e to the power minus at to decay to 37% of its initial value. Alternately, from equation 4, the time constant is the time it takes for the step response to rise to 63% of its final value. So you have to move on to the 63% of its final value. Okay. So 1 over a is known as the time constant. So remember this, 1 over a is the time constant. And what does it mean with that 37%? It means the time for e to the power minus at to decay to 37% of its initial value. Alternatively, you can say that the time constant is the time it takes for the step response to rise to 63% of its final value. Okay. So 0 to t, 1 over a is the time constant. And see here 63%. That is the first order system response to a unit step. Unit step means what? That means you give something like that. That is your input. That is your input signal. That is your input signal. You give something like that. And for this input signal, you get the value. So first order system response, so 0.63 here, come here. 0.63 come here. So 0.63 means 1 over a. 1 over a. And 0.9, that means that is the time response, the response time. TS means the settling time. That is the time constant. 1 over a is the time constant. Okay. So see, initial slope is time constant. It is 1 over a. Let's move on. Some other things are given like rise time, TR. The rise time is defined as the time for the waveform to go from 0.1 to 0.9 of its final value. Rise time is found by solving equation 4.6 for the difference in time CT 0.9 and CT 0.1. So rise time is the time required time gap between 0.9 to 0.1. So finally we can get this 2.2. So how it comes? See, 0.9 and 0.1. See, here is the 0.1 value and here is a 0.9 value. The difference of these two is the rise time. So difference of these two is known as the rise time, which is the 2.31 by A minus 0.11 by A. It is 2.2 by A. Okay, that is the rise time. Okay, you understand?
Yes, sir.
That is the interesting one, rise time. These are simple actually. So if you remember the formula, you can calculate the math. And settling time is the 4 by A. So move on the figure 4 by A. That is the settling time from 0 to 4, the point at where it settled down. That is the 4 by A. Okay, so settling time. These things. Now I think you will get the problem here. Okay. Now let's look at a skill assessment exercise 4.2. There is a problem. Let me show you how to solve it. Today I will finish chapter 4, then one more chapter will be left. Okay, that is the chapter 3 for the midterm.
Okay.
Okay, so in the next class I will solve the chapter 3.
Okay. Okay, sir.
So in the next class your midterm syllabus will be covered. Then
Okay.
the next Thursday you give a quiz.
Inshallah, sir. Okay.
Inshallah.
Okay, sir.
Okay, everyone, listen, everyone. Next Thursday you will have a quiz.
Next time.
Okay,
Hello,
sir.
sir.
How
After 1 week. After 1 week.
How many
Yeah.
questions?
All up to chapter 4.
Only.
All, not only 1 to 4. Because
Chapter
you are getting 1 week, and today I will uploading all.
Yes. Okay, sir. We are ready.
Upload procedure.
Yeah, I will uploading all. Then you can take the preparation for the
Okay, sir.
midterm also and for the quiz also
Okay,
at
sir.
a time.
Thank you, sir.
Okay.
How many questions?
What is the midterm date?
I don't know.
Still, I do not know also because the routine has not published yet.
Yes, it's coming. We are waiting, sir.
Okay, maybe soon, very soon you'll get the midterm date.
Inshallah.
I think.
Already.
Okay.
We prepare squeeze.
Okay.
Okay, sir.
Now look at the question here. What they ask. A system has a transfer function gs is equal to 50 by s plus 50.
Okay.
That is your transfer function. Okay. Now find the time constant Tc. So what is the formula of Tc? Anyone? Do you know what is the formula? 1 over a.
1 over, yeah.
1 over a.
T-
So here a is 50. So 1 over
Fifth.
50. So what is the result? Maybe 0 0.02. 0 0.02 second. And settling time.
Settling time.
Settling time, that means Ts. I think it is 4 by a, right?
4 by A. Okay.
So that means 4 by 50. So what did become? 4 by 50.
0.8.
Can you check it? Do you have the soft copy of the book or not? 4 by 50. Yeah, 0 0.08. So that is 0
You're right,
0.08.
sir. 0.8.
Yeah, 0 0.08 second. Again, rise time TR
2.2.
2.2 by A.
Yeah.
2.2 by A. So what does it mean? 2.2 by 50. It becomes 0 0.04. That's it. Simple one. Only you need to remember the formula.
Formula symbols. Yes.
Yeah, all the formula, then you can do it. Okay. So I think I can proceed. So it is skill assessment exercise 4.2.
Okay, sir.
Now second order system. So what is the second order system? In the second order system, see this thing come. The power of the S would be 2. Maximum power would be S square. Second order system. Second money 2, power 2. So equation would be look like this: S square plus S plus B. Something look like this. Okay. Now I'm moving on. See now the general second order system. The general second order system is given here. We have okay. Let's see, a few things we need to remember. A natural frequency. The natural frequency of a second order system is the frequency of oscillation of the system without damping. See, without damping. That means without getting any resistance. Okay. That is the natural frequency omega n. The natural frequency of a second order system is the frequency of oscillation of the system without damping. The example, the frequency of oscillation of a series RLC circuit with the resistance shorted would be the natural frequency. RLC circuit, see, it is a source, say, that is L, that is C, and that is resistance. That is the RLC circuit, right? L, C, R. Now, if you short this one, short the resistance, then what would happen? Now, the frequency of the oscillation of a series RLC circuit with the resistance shorted would be the natural frequency. So that would be natural. Just said this one. And another term, which is the damping ratio. See, before we start the next definition, some explanation is in order. We have already seen that a second order systems under damped step response is okay. A system whose transient response goes through 3 cycles in a millisecond before reaching the steady state would have the same measure as a system that went through 3 cycles in a millennium before reaching the steady state. For example, the underdamped event curve in figure 4.10 has an okay. Okay, so that is the damping ratio zeta. Exponential decay frequency divided by natural frequency radian per second, or 1 over 2 pi is equal into natural periods per second divided by exponential time constant. The damping ratio zeta can be right like this. So now consider the equation, general equation. GS transfer function is equal to GS is equal to B by S square plus S plus B. Okay, from here we'll show the zeta and omega n. From here we'll show the zeta and omega n. Now, if A is equal to 0, if A is equal to 0, then it would be B by S square plus B. Now here, the value of omega n would be square root of beta. Square root of beta. Omega n would be square root of beta. And A is equal to 2 zeta omega. So finally, in terms of omega and zeta, we can write like this. GS is equal to omega n square divided by S square plus 2 zeta omega ns plus omega n square. From this equation, we can say that these 2 zeta omega n, that is actually A. And omega n square, that is actually square root of B. This will be not x square root. It is actually B. Okay. Omega n square will be P. Okay, so we get this one. From here, we can draw some kind of conclusion. Now see another example. Finding zeta and omega n for a second order system. So you have to find out the zeta and omega n for a second order system here. Zeta and omega n for second order system. Now from this equation, see here. 2 zeta omega n is equal to 4.2. And omega n square is equal to 36. So omega n would be 6. Now put here zeta is equal to 4.2 divided by 2 by 6. So I think it would be 0.35. What would be the value? 4.2 divided by 6 divided by 2. Yeah, 0.35. The value is 0.35.
1.35.
Right, you understand how it comes? That is 2 zeta omega n. And this term is omega n square. Omega n square 36, omega n equal to 6, and 2 zeta omega n equal to 4.2, zeta is equal to 0.35. Okay. You clear this problem?
Yes, sir. Yes, sir.
Okay.
Understand.
Okay, now see some figure. That is important to do a math. See, conditions. Whenever the value of zeta would be 0, then your pole would be on the j omega axis. Pole would be on the j omega axis. And the output step response should be like look like this. That is known as the undamped. Undamped. And whenever the value of zeta would be in between 0 to 1, less than 0, less than greater than 0, less than 1. In this case, your pole position would be look like this, and the curve would be under damped. And if zeta is equal to 1, the curve would be critically damped. And if zeta is greater than 1, then curve would be look like this. Okay.
Okay, sir.
Now in the next question, you will have to find out the value of zeta and determine the curve. What would be the curve type? And you have to draw it. Okay. Now that's example 4.4. Characterizing response from the value of zeta. For each of the systems shown in the figure, find the value of zeta and report the kind of response expected. So you have to find out the value of zeta and find out the output response type. Now see from the first one. See omega n square is equal to 12. So omega n would be what? Square root of 12. What is the value? Anyone have any idea?
Yes, sir.
Square root of 12 means 3.46. 3.46.
3.46.
46. Now 2 zeta omega n is equal to 8.
8.
So zeta would be what? 8 by 2 into 3.46. Okay, I have a call. Let
Yayo, aynaba kulmiya ku batay. Yayo.
may waan yaabanahay dad inta codeeyay dhahaya
Wallahi u tii sax kulmiya ku daay sax. Wadari waa galbaday. Ka waa ka soo wadan. May Abdullah Warad.
orado xisbigiini meel ku sheeg orado xisbigiini yaraaye weli laysma gaarin hayaay halaysku yimaado tuulooyinka ayaa lagu wareegin
Ayda lahayd tuurooyinkii galbeedka halaysa ayaa barigii waa la city.
war waxaas waxa ka weyn 6 gobol waaweyn baa isugu imanaya dowlooyinkeeda awbe
oo maxaa 6 gobol waaweyn maxay ku haysaa wallahi billahi tallaahi waa la ka tirsanaya burca mooyaane
ood weyne markas ood weyne
hal qof dheereeyay sigri
6 iyo 4 bay ahayd iskii wallahi 6 iyo 4 bay jiblaad waxaan kala dalaba laba
isdheer kulmiyo wuxuu leeyahay 740 cod buu leeyahay ama shaqadeeday almost ku leeyahay 12 cod buu dheeri almost
wali lisma gaarin ciyaar waa gali dambe oo
yaala ma kolba uu 30 xildhibaan dhaafaysa
okay, now see. Now zeta. Now find out the value of zeta. 8 by 2 by 3.46. So what it becomes? Let me check. Do you have calculator?
No, sir. Yahya calculator. Wait, sir. Wait. Yes, sir.
You need a calculator all the time because
yes,
it's math.
Yes, sir. Yes, sir.
I'm gonna calculate it.
1.15. Value is 1.15.
Yes,
now
sir. 1.15.
Yeah. Now see, this value is greater than 1. Now what kind of output would be? 1.15. Now look at the previous figure. Value is greater than 1. So it would be overdamped. Overdamped. Okay. So you will write that since the value of zeta is 1.15, which is greater than 1, the time response curve would be overdamped. It would be look like this. Just draw something like that. Okay, that would be the answer. Overdamped. Similarly, you have to do others. Okay, so I will not show you now, but you can do it, I think, right? Can you do it?
Yes, sir, I'm gonna do it.
Yes.
See, in the first one, since it is
they are all same.
1.155. See,
so okay.
Overdamped. And second one is it would be 1, which is the critically damped. Third one, it would be less than 1, which is the underdamped. So second one is if it is 1, if zeta is equal to 1, then it would be critically damped.
Critical damp.
Yeah.
If it is less than 1, then it is underdamped.
Underdamped.
So you check this. Just do the calculation and check here. Okay.
Okay, sir.
Okay. So similar thing happen for each of the transfer function in it's 4.3. Find the values of zeta and omega n and the nature of the response. 4.3, that means previous example for this. Okay. Skill assessment 4.3. This is example. Skill assessment 4.3 means this one. For this one. For this one, you can also find the zeta and omega and find the response, output response. Okay. You also check this one.
Okay.
Okay. Also check 4.4. Exercise 4.4. So I will not show you because it is same. The same thing. Find out the zeta, find out the omega and say what kind of system response it would be. Right. Move on. We are moving on. See here the another topic that is underdamped second order system. In the underdamped second order system, here on a few things like rise time TR, peak time TP, the time is peak. This is the peak time. The maximum. Whenever it goes to the maximum, that is called the peak time. Percentage overshoot. That means the amount that the waveform overshoots the steady state or final. And the settling time TS. See peak time, the formula of the peak time is this one, pi by omega n square root of 1 minus zeta square. That is the peak time formula. And the percentage of overshoot formula, this is. The thing is C max, that means the maximum minus final divided by final. Now look at the figure. C max and C final, that is the final. Okay, C final. C max by C final, C max minus C final divided by C final is the into 100. It is the percentage of overshoot. Or you can find out the zeta here like this. Minus ln percentage of overshoot by 100 divided by pi square root of pi square plus ln square percentage of overshoot by 100. Okay. And now see, it is the curve from which we can find out the percentage of overshoot and the damping ratio. So see, if you know the damping ratio zeta, then you can find out the percentage of overshoot from the curve. Let's say you have the damping ratio 0.5. So move on here, this point. Now, what is the value of this? Here, something like here, maybe 15%. Percentage of overshoot is 15%. Like this, from the curve, you can also find out the value. And settling time here, 4 by zeta omega n. And rise time here also, you'll find the rise time. Normalized rise time is here. Say for the damping ratio, zeta, the rise time is here. Rise time into natural frequency. That is the rise time into natural frequency. Okay, now last problem of today's class. Finally, this is going to end this chapter. Okay, see the problem. Given the transfer function,
Okay.
this one. Now, question is find the TP, that means the peak time, percentage of overshoot, settling time, and PR. This thing you have to find it out. Now, see what is the TP, value of TP. Pi by omega n into square root of 1 minus zeta square. All right, that is the value of TP. Now you do the calculation here, and percentage of overshoot TSC. Omega and zeta are calculated as 10 and 0.75. Let's find out the omega and zeta. Say that is the omega n, and that is the zeta. Now substitute zeta and omega into equation. Oh, those equations. TP, percentage of overshoot, yes, so you can find out easily. Now time to find out the response time. For the response time, you need to use the table. Using the table in figure 4.16. Now, look at the 4.16 table here. Now, what is your damping ratio? Zeta. Zeta is 0.75. Now, see, zeta is 0.75. That means zeta is in between here, 0.7 and 0.8. So, normalized rise time would be middle thing. Add these two and divided by 2. Then you will get the value.
Okay, sir.
Okay, so TR 0.23 second. Rise time is normalized rise time is approximately 2.3 second. Dividing by omega n, it yields 0.23 second. So if you get the normalized rise time, then divide it by the omega n, then you will get the TR. See, from the table, you will get the normalized rise time. How to find this normalized rise time? See, this is 0.75 in between. That means 2.126 plus 2.467 divided by 2. So what you will get? 2.126 plus
2.29.
2.9, right?
2.29.
So 2.29.
29. Let me check again.
Okay, whatever. 2.29 means 2.3, right? 2.29 means 2.3 actually, right? 2.3. Now divided by 10 because omega n is equal to 10. Natural frequency 10. So it would be 0.23.
Yeah.
That's it. 0.23 second. Okay, so understand this one, this problem. Just you need
Yes,
the
sir.
formula to calculate. Okay, so I think that is end of this chapter.
How do you find the TB set? TB.
Oh, TP.
Yeah.
TP.
Yes,
TP has a formula. This one.
Oh.
Now calculate this. TP is pi by omega n square root of 1 minus zeta square. So omega n and zeta. Okay, just use the formula and match.
Okay.
Okay.
Okay, sir.
Okay, so that is the end of your chapter 4. That is the end of chapter 4. Now I need to take your attendance.
Hello, sir.
Okay, sir.
Yes.
স্যার ভার্সিটিতে স্যার ক্লাস নেওয়ার বিষয়ে কি যেন বলতেছিলেন স্যার, জয়েন করতে একটু লেট করছিলাম, শুনতে পারিনি।
ভার্সিটিতে ক্লাস হবে আর কি এখন থেকে রেগুলার। পারবা ক্লাস করতে পারবা?
কবে থেকে?
ডেটটা জানাবো আর কি পরে, মানে আমরা চিন্তা করতেছি। আমাদের চিন্তা ভাবনা
রেগুলার ক্লাস হবে?
এখন তো ল্যাব ক্লাসগুলো হবে, ল্যাব lab class. We are thinking to take the lab class in the campus, on campus. What do you think? What is your opinion?
স্যার এত দূর থেকে যায় ল্যাব ক্লাস করা শুধু?
কোথায় আছো তুমি?
স্যার জামালপুর।
জামালপুর?
স্যার 200 কিলোমিটার।
200 কিলোমিটার দূরে?
স্যার 180। স্যার বর্ডারের সঙ্গে একদম বক্সিগঞ্জ বর্ডার আছে না স্যার, জ্ঞানগঞ্জ?
হ্যাঁ
স্যার জ্ঞানগঞ্জ।
আচ্ছা দেখি ওটা জানাবো না পরে। Okay guys, now let me take the attendance.
Okay, sir. We
Okay.
take
1